Welcome to EE 597 with Professor Krishnamachari on Wednesday, June 1st, 2016.
Okay, so let's do a little bit of a recap, as always, of what we were discussing the last class or so, or in fact last few classes. So we've been talking about the file layer, and I'm hoping today to really wrap up with that so we can focus on the higher layers. We've talked about digital communications in standard AWGN channels. We've talked about fading and RF propagation. And in particular, two models for this that we've examined are the simple path loss with log normal fading and a discrete Markov chain model for fading. And we've talked about how do you quantify performance under wireless fading channels. And two metrics we introduced were the expected probability of error and the outage probability. And just to refresh our memory, the way we figure out the expected probability of error is that if you know the probability of error at any SNR, but now under fading SNR itself is a distribution with some PDF G gamma, then we're basically integrating this. That's the notion of expected probability of error. And outage probability is basically you take your fading distribution and you say that the probability that your SNR is below some threshold, theta outage, that's the outage probability. So in both of these, in this case, the outage probability comes from the performance function that's describing how your particular modulation scheme works, and in this case it's explicitly there in the expression. And then the G is capturing the environment. So in either case, the performance depends on the environment, which is what G gamma is describing, which is basically a PDF, right? So it's a stochastic environment. And the underlying communication scheme, okay, whose performance is being given by f of gamma. So this is the probability of error for that scheme. The communication scheme, so far we were focused on primarily modulation, but the scheme could also include, we talked about error control, coding, or something else on top of that. So, as we sort of think about models of fading, the simplest models focus on kind of IID fading. What this means is that over time, let's say the SNR, the receive power, is being drawn in IID fashion from the G gamma distribution. Okay? So I say receive power or SNR because for all intents and purposes, SNR is basically the receive power over the noise. Right? That's what SNR is. So this is just, if you assume that the noise power is a constant, these two are basically just related by a constant. So whatever the distribution of the SNR is, the distribution of the receive power is just that constant scaling factor. So it doesn't really have a different distribution other than the scaling factor. So if we look at IID fading, the example we looked at was log normal fading, in which we're describing this distribution G of gamma as a log normal random variable. But there's nothing magical about a log normal random variable. It happens to be something people took a bunch of measurements and found seemed to be a good fit. Right? You could potentially look at some environments and find something else that fits well. In fact, there are many other distributions that are typically used, such as something called the Rayleigh distribution, or something called Ricean distribution. There's also something called Nakagami M distribution. They're just different distributions people have found to be good fits for different environments. For the purpose of this course, we will largely use the log normal fading just for simplicity more than anything else, because it's a Gaussian in the dB scale. It's very easy to work with, easy to express some of these parameters in terms of the Q function and so on. So one thing I wanted to mention is that in the homework, too, there's a problem asking for I think it was the outage probability with a log normal fading, right? And so if you're thinking about it, basically the outage probability is the probability that your gamma falls below the outage threshold, right? If I look at this in the dB scale, that's exactly the same still, right? Whether it's in the dB scale or in the original scale, the equation is really the same. You just have to transform both of them by into the dB scale, because the decibel scale is just a monotonic transformation. It's not changing the relationship. And in this dB scale, the gamma dB, that's a Gaussian random variable, right? So the CDF of a Gaussian, this can be expressed as a Q function. Okay? And so when you're working that problem, I would urge you to kind of think through what is the CDF for a Gaussian and write it as a Q function. Right? This probability can be expressed in terms of the Q function. Okay. If you're not familiar with the Q function from 503, sometimes depending on which section you took, you may have had a deeper or less deep introduction to Gaussian random variables. Just look it up. There's plenty of information online. Basically, all it is the CCDF of a standard normal variable, meaning that the Gaussian for which the mean is 0 and the standard deviation is 1. But in general, when we're describing our variance here, it's still 0 mean for the additional term that we add, but the SNR has also the received mean path loss component, which you get from the simple path loss portion. So that means that the mean is actually shifted to whatever the received mean power is. So the mean itself is not 0 for the SNR. And secondly, the variance is something that's given to you. In the problem, we actually give the number for what the variance is. So it's not a standard normal. So if you have a random variable that's Gaussian, that's not a standard normal, then you have to scale it by shifting it by the mean and dividing by the standard deviation to get the standard normal. So just quick comment. If you have some random variable x that's distributed as a normal random variable with mean mu and variance sigma square, and you shift x by the mean and you scale it by the standard deviation, then the variable that you get, let's call that y, this is distributed as a standard normal. Okay? So this is the scaling. Standard Gaussian or normal random variable. Okay, so this is the one thing you might need to recall from 503. So other things, I guess I was still continuing to talk about. So we talked about IID fading models in which this G gamma is just a distribution. Every time you get the SNR, it's like it's drawn from that distribution, independent of whatever the value was before. So in an IID model, by definition, there is no memory in the process. How strong or weak the signal is right now has nothing to do with the past. Okay? And as a model, you can imagine that that's not very realistic. You might expect that over time, when you're observing the SNR, that it's not completely independent of your previous sample, especially if your previous sample was not that long ago, right? So that's part of the motivation to look at, for example, that Markovian model. But there are other models, again, which incorporate some memory. So you can add some kind of a memory basically by saying that your SNR process, so for now, let's assume we are only interested in discrete samples in discrete time. Why is that reasonable? Because when you typically measure an SNR on a link is when you receive a packet, or at some granularity that's a function of what communication system you have. You're typically not interested in the SNR process as a continuous process. It is a continuous process, it's just you're not interested in it as a continuous process. You typically sample it at some discrete times. So if you think of it that way, you think of your SNR measurements as some kind of process xi, where xi starts from 0, 1, 2, and goes on forever. Each number here just says what was the time at which you took that sample, right? So this variable is just a random variable for each time. But if you have a sequence like this, this is what we call a random process, right? In 503, you all learned about discrete time random processes. And in general, the way you describe fully a discrete time random process is by giving its joint distribution for all times. Like you would actually have to say, what's the probability that x0 is this value, x1 is this value, x2 is this value, x3 is this value, and so on. And that gets really cumbersome. A really arbitrarily large memory and an arbitrary process is very hard to do anything numerical with. It's very hard to make analytical predictions with, and so on. And so when we work with these models, we try to pick something that's simple and workable. Okay. One such model, and again, not the only such model, but one such model is the discrete time Markov model, in which we can simplify that if you look at any particular observation at some time and say, what's the probability it's this, conditioned on previous values being certain values, that you can simply express it as conditioned on just the most recent observation. So it's as if, regardless of what happened in the distance past, if I just know what happened in the last time step, that's enough for me to decide what the distribution for now is. Okay, so that's the Markov chain. And if we say, moreover, not only do we say that the time is discrete, but the values that the SNR is going to take on are themselves going to be put into some discrete bins, then we'll have a Markov chain with discrete states or finite states. Right? So a further simplification. So already saying that you're talking about a Markov model is simplifying the random process that the SNR might be. Okay, let's even start from the beginning. First of all, we're choosing only to look at it at discrete times. Second, we're saying not a general random process, but a Markovian process, which means that the memory is somehow limited to one time step. Moreover, we can further simplify by saying that the xi for all I are in some set of values where S is a finite set. Right? So in this case, we get a discrete time, discrete state, Markov chain model. So this gives a discrete time, discrete state Markov chain model. And we looked at this example last time of just the simplest such, even further simplification would be there's only two values, right? So this is literally like the simplest model we could imagine for a fading environment that has memory, where you can talk about sort of the dependence over time of the SNR process. So, and we derived certain properties of this two-state Markov chain. So the purpose of this model is just to capture a little bit more realism, but at the same time we are simplifying it also, right? By just choosing two-state, we're saying either the channel is good or bad, and that simplification is similar to talking about outage. It's like putting a threshold and saying either the SNR was above that value or below that value, right? And so you can think of this as a bad state or an outage state, and this as a good state. But again, this is not the only model. You can imagine having more states than just two. You can have 5 states. You can say the channel was really bad, it was okay, it was good, it was very good, right? And for each of those states, you might say, if it's within these SNR ranges, I'm going to say that, right? One reason you might want to go to more states is if your radio, for example, allows you to switch to different rates depending on what the SNR range is. So if you have a radio that you can say, it operates at very high data rates if the SNR is extremely good, some medium data rate if it's just okay, sort of low data rate if it's okay, slightly worse data rates if it's poor, and just not at all if it's really bad, right? Now you have a 5-state representation, and that's useful to you because you're intending to operate your radio in those 5 discrete SNR ranges. So that's an example of why you might have more than 2 states. It's still not a perfect model because it is only capturing memory of one time step. It's somehow saying that there is no, for example, periodicity to the channel. So if you have some environment in which the channel exactly every 100 milliseconds looks bad and the rest of the time it looks good, that may not be trivial to model as a Markov chain. Why? Because let's say your time granularity, let's say you have a environment which is sort of bad every, I chose some number at random, I think it was 100, but all of these times it's sort of always good. Okay. So if you have a channel that somehow is behaving very deterministically, a Markov chain is not going to capture this behavior. Because in a Markov chain, the probability that you go from good to bad is the same at every one of these time steps. There's no way to build into the simple Markov chain the fact that for 10 time periods in a row, it's going to be good for sure and then going to go bad. Right? A Markov chain doesn't, at least if it's of order 1, which is you're only looking at the previous time step, there's no way for you to model a deterministic channel like this using the Markov model. It is a channel with memory in that if you kind of keep track of how long it's been since the channel went bad, you could tell when it's going to go bad again. There is memory. But now the memory is not one step. The memory sort of goes back to a window of about 10. Right? If you want to model an environment like this as a Markov model, one option would be to treat as your state the measurements for 10 consecutive values. Right? So you might have seen this in 503, which is that you can always create a higher order Markov chain in which what you say is, I want to say that the value now depends on the last 2 time steps. And one way I can model that is by increasing my state representation to say what was the value in the last time step and what was the value in the time step before that. Okay. So, but now the price you pay for this is that the number of states is going to go exponentially. So if I want to talk about what happened in the last 10 time steps, whether it was good or bad, now I need a binary vector of size 10. So I have 2 to the 10, 1,000 different states that describe what state I'm in. And each of those states would say what was the channel in the last 10 time steps, right? So there's a price you pay for trying to capture more memory in a Markov model. Okay. And we'll come back to that point as well. So again, going back to the homework, there are problems of fitting model parameters based on real and simulated data. There's one set of real measurements we took in RTH just across the street here. On the 4th floor, we just had a Wi-Fi receiver measuring what the measured RSS value, which is the receive power value, is at different positions on the floor, and with respect to different access points. Okay. And so we have this data set from which you can extract, and we know the positions of the access points and where the receivers were, so you can figure out the pairwise distances. And so you can basically take that data set and imagine that you can plot, and for the simple path loss with log normal model, and in fact just for the simple path loss model, if you were to plot the received power as a function of the log of distance over the reference distance, we said that it's basically a straight line whose slope is the path loss exponent. Okay. And sometimes we refer to this receive power as RSS. So if you see the phrase RSS somewhere, you're not thrown off. But really what you'll get from that data set, the raw data, is a bunch of points. Okay, so you'll just get a bunch of points, and that's the data. Each point you can plot because you will know the pairwise distance between the access point and the receiver that measured it. And you'll know what was the measured value. This is if you're in the dB scale. I should have mentioned that. So if you're in the dB scale, and this is in the log scale, it's a straight line. So you will know for each pair of points from the data set what was the distance, what is the measured value. So that's what you're using to generate the scatter plot. So what the problem asks you to do is to figure out from the data set what the slope of the best fit line is and what is the variance associated with the log normal fading component. Because that statement says that once you have this line, if you kind of were to take a vertical slice, it looks like a Gaussian. No matter where you take the vertical slice, it looks like a Gaussian with the same variance. And the question is, given that data, what is that variance? Is that clear? What the question is asking? So how do you do this? So the first thing you would need to do, if you haven't done before, is use linear regression. Okay, to compute the best fit line. linear regression is a well-known technique. If you're using, for example, Matlab, it's a built-in function. You can look it up online. Implementations are very easy to find and use. So you'll get the best fit line, and the slope of that line will tell you the path loss exponent. Moreover, the y-intercept of this is the p transmit plus k dBm, where the k is the path loss at reference distance. When distance is d0, then log of d over d0 would be 0, so that's this point over here. At that point, that would be the mean path loss, right? So that would be this value, yeah. Sorry, k is not... yes, because it's unitless without that. Yeah, thank you. Yeah, that's a good point. So if you know the transmitted power and you know the received power when the d is at d0 in the y-intercept of this line that you find the best fit line, at that point, the measured value, if you know this and you know the received power, then you can figure out what kdB is. So that way you can figure out also the kdB. Right? Best fit line. So the slope will yield eta, y-intercept will yield kdB. In the data set, we asked you to just assume that the reference distance is 1 meter. So you've got all of the parameters corresponding to the simple path loss model. Now to figure out what is the fading additive term that we have, we say that it's a zero mean with a certain variance. So here's how you think about it. So this is the mean path loss. Each one of these is a random sample. If I subtract out at a particular distance, so let's say I was at this distance for this particular sample, if I subtract out the mean path loss from the random sample, then what I'm left with, that's the additive log normal sample, right? With mean 0. Why? Because I've subtracted out the mean. Right? So it's biased up or down by this mean path loss. But if I subtract out that mean path loss, then what I'm left with is just the fading term, okay, the additive fading term in the log normal case. So if I take every one of these samples and I subtract out wherever the line is at that corresponding distance, then I'll be left with a bunch of samples that are really supposedly samples of that log normal random variable that I care about, right? So subtract mean path loss from each sample corresponding to the right distance. Just to clarify what I'm saying here, the mean path loss is not the same for every sample. It depends what distance you took the sample. When you find the best fit line, you're saying what is the mean path loss at different distances. So at this distance, this is the mean path loss. At this distance, this is the mean path loss. So for each sample, you want to remove the right amount of mean path loss corresponding to the distance. So once you do that, you're left with random samples that should be normally distributed with mean 0. Okay. Now, is it going to be exactly mean 0? Probably not, because there may be some biases, and we'll talk about, in fact, that's one of the questions in the problem set, but roughly speaking, this is what you should get. One reason why it won't be exactly mean 0 is that you didn't actually take at every distance all your samples, take their average and remove that average value, which would give you mean 0 for the samples. But what you've done is you've taken a best fit line, which is incorporating the average values for other distances as well. And so you might see a little bit of, for these particular samples, the mean might be a little bit above 0, a little bit below 0. But in principle, if you take all of these samples together, the mean value should be close to 0. And when you take these samples, their variance is going to be an estimate of sigma square in dB. in this is the fading variance we're talking about. So basically the variation of these things around the mean path loss value. So this is one particular approach where you start with the data set and you infer back what is the model that you have, right? Now, why would we even do this? Why bother fitting a model to the data? We already have the data. Why do we need a model? Why do I need to know these numbers? What could we do with these numbers for that model? You're basically characterizing the environment, right? And in particular, your samples might be sparse, meaning you may not have samples at every distance. For whatever reason, when you took the measurement, you only had 4 places where you could take measurements. In our example, maybe 8 places or so. The building is much larger than that. You could be at many more distances, many more positions. So how do we predict what things might look like at those other positions? So by fitting it to a model, we can then extrapolate beyond the measurements we have. So that's one usefulness of a model, right? And as you mentioned, you're basically able to characterize the environment. And in particular, it means that by having this characterization and knowing what we know about how to model the outage probability, how to model the expected probability of error, we can then do calculations that tell us what do we expect the performance to look like for links at different locations in our environment. Right? So this is an exercise in basically taking some set of measurements, using the measurements to find the parameters of a model, and then once you have a model, you can use that model theoretically to derive certain performance measures, and that helps you guide your design maybe, right? Or helps you understand what your network is likely to perform, how it's likely to perform. These things are not just of theoretical interest, they're used in practice. For example, I've consulted for companies where they'd come up with a network protocol that was for a mesh network for building automation, and they wanted to know how well will their performance be. And they had a very specific threshold for outage, and they knew that if the SNR fell below this value, they were going to be an outage. They needed to know what fraction of their packets are likely to be lost because of these outage conditions when they deploy a network. The problem was that they had about a week to ship their product. They had to write some documentation that described what the performance would be and also advise their customers on how far apart nodes should be placed so that the outage probability would be reasonable. But they wouldn't even know where people would deploy their products. They might deploy it in a home environment, they might deploy it in a factory environment. And so one thing that they could do is to figure out what are typical values of these fading parameters, such as the variance, the path loss, in a factory environment, in a home environment, in an office building. And people have done these measurements in the literature. And for each of those cases, they can kind of predict what would the outage probabilities be and what should be the minimum spacing between nodes so that your outage probability is the right value. And so it's actually a very important part of deploying a network is thinking about what the performance of your network is going to be. And you may or may not be able to measure these things after they're deployed, but being able to predict in advance that things are going to look really bad in certain environments, and therefore you might need to place your nodes closer together. In other environments, it's okay to place them a little farther away. So those are some of the kinds of things you might need to use it for. For cellular networks, typically before they deploy base stations, they do some cell tower studies where they try to look at different locations and try to understand what would be the performance if I placed a cell tower at this corner versus another corner. They can't take measurements everywhere in the city. They can take measurements from certain places, and from that, fitting into a model, they have to extrapolate what would my cell size, what would my coverage look like, and then decide where to place things. So these models really play a role in making decisions about how to deploy a network. Okay. So one theme that I mentioned we're going to come back to over and over again in the course, and this is exactly what we've been talking about, is we have some real-world environment, okay? And the real world environment is uncertain, right, or noisy. And we can take measurements from the environment, or samples, if you will. And we can take some model of reality, which is not reality, and through the process of fitting, parameters to these measurements, we can figure out the parameters. So that process of going from the measurements to the model, figuring out what parameters you should have for the model. Sometimes it's called statistical parameter fitting, or more generally, that's statistics. When we say probability and statistics, statistics is the part of all of this where you take real-world measurements, real-world data, and you try to infer from it something about a probabilistic model. You ask questions like, what's the mean, what's the variance, what is the slope of a certain linear relationship. You might look at, for example, if it's a Markov environment, you might figure out the transition probabilities. So figuring out what should you choose for these parameters in your probabilistic model based on real data. That's statistics, right? And then your model of reality, which in most cases, if it's an uncertain, noisy environment, is going to be some probabilistic model, right? So for example, it might be a random variable, it might be a random process, and you might have a particular, like we have talked about already, a specific distribution in mind, a specific process in mind. All of that is the modeling, right? Now, there is no guarantee that your model is reality. In other words, that your model perfectly captures everything about the real data set. So there's always a little bit of a trade-off where you take a model and you want that model to be as realistic as possible. On the other hand, if you made it extremely realistic, it becomes very hard to compute, it becomes very hard to use, it becomes very hard to actually do anything with it. So there's always a tension. When you're doing analysis, prediction, simulation using a probabilistic model, you want that model to be simple. On the other hand, in order to best fit the data that you have, you want the model to be complex. So there's always this tension, right? So ultimately, there's a little bit of an art in selecting the right kind of model. That's simple enough that you can do things with it, but complex enough that it can capture reality really well. Right? So that's always kind of, maybe you can think of it as the art of modeling. Right? So if it's too simple, or let's just say, if it's very simple, then it's easy to work with, compute, but maybe less realistic. On the other hand, if it's a complex model, then it is more realistic often. Of course, not every complex model is more realistic, but if you want more realism, often you have to increase the complexity of your model, but it becomes hard to compute. Okay. Just to give you a very concrete example, we talked about consider a Markov model with memory of 2 steps. Okay. Sometimes called a second order Markov model. So a second order Markov model, you want to say something like the probability of xi plus 1 equal to xi plus 1, condition on the entire past, can be described by what happened in the last 2 time steps. Okay, so it's called a second order Markov model. It's almost like a Markov model, except now each state needs to describe what happened in the previous time step as well as the time step before. Okay? So if we just take a 2-state model, like each time step it's either good or bad, but now to describe all of the possible conditional probabilities, I have to consider pairs of what happened. Like what happened now, what happened the time step before. And then that'll affect what will happen next. Right? So now the model, even with just a good and bad state at each time, looks like it has 4 states. So you can just imagine every combination of these are now possible. Right? So even though at each time step we're saying the channel is only good or bad, if I want to describe it more realistically to capture dependence over 2 time steps, I need to increase the number of states in my model from 2 to 4. Similarly, if I wanted to do this for the last 3 time steps of history, I can do that, but now I would have 8 states. And the number of states is going to grow exponentially. And as I grow the size of the model, I'm getting more and more realistic description of reality. Maybe reality has a very long memory. Right? Maybe what happened a second ago will affect the performance now for whatever reason. But in order to capture that in a Markov model, I might need such a high order that the state space being exponential in that order is going to go completely crazy. Like maybe just to model, a good and bad state, I have to have thousands of states or millions of states in my Markov model. And so that's an example of how the complexity of the model versus the realism is always the tension. Right? So then there's an art of the modeling. How far back should I keep this? If I go too far in one way, I can't compute. If I go too far in the other direction, it might be very unrealistic. In fact, you can think of the IID model as an even more special case in which it's only 2 states still, but the probabilities of going from a 0 to a 1 or going from a 1 to a 1 are both the same. So if I say it doesn't matter what the last state was, whether it was 0 or 1, the probability of going to 1 is the same, that's just the IID model. Right? That's even simpler. Why is that simpler? Because now to describe this process, I don't need 2 numbers. I don't need a P01 and a P11. I just need one of them because they're both the same. Right? So now the model is even simpler, but it doesn't have any memory in it at all. Right? So that's the trade-off that's inherent in probabilistic modeling always. So there's some real world. We have some probabilistic model. We're going to fit, based on the real world measurements, some attribute of the probabilistic model. Once we have a full probabilistic description, I tell you this is the model, these are the parameters, I can then do mathematical calculations, right? They could be closed form calculations, they may be MATLAB simulations, but the point is I can now do things with it, right? And so we can use this model to do for performance analysis, for design, and for evaluation. Right. So you have this model. Once you fit all the parameters, you can say, if these were the parameters of the environment, this is how my comm system is going to work. Or, given this is the environment I have, this is how I should design my comm system to do best in that environment. Okay. So I forget now whether it's in homework 2, and if it's not in homework 2, it'll be in homework 3. If you know, for example, that it's a 2-state Markov chain, you can ask the question, how long should I wait before I retransmit a particular packet? Right? That's a design problem. I can solve that design problem if I know what the Markov model is and I know the parameters of the Markov model. Right? In the example of figuring out the outage probability for a log normal random variable, we're using the model fitting parameters to that model to tell us the performance of a communication system in that environment. Right? So all of these things become possible if we can go through this process. Right? But one thing that you might lose sight of is that this process of starting from a model where you know all the parameters and then figuring out things about it, this is what 503 was all about. Right? But what 503 really didn't get to is how do you choose a model? Like, why should it be this distribution and not that distribution? If it's a Markov chain, who gave you the transition probabilities? Right? So the point I'm trying to make here is that the choice of the model, there's just an art to it. You can be creative. You can try things on your own. You don't have to look it up in a textbook. Right? You can look at the data and say, looking at this data, it doesn't look like log normal to me. If I fit it to this other distribution, I think it'll be a better fit. That's up to you. Right? And you have to justify to someone that based on the data, this is why I concluded that this is the better model. How do you fit that model based on real measurements? That's the job of statistics. Right? If you take, for example, we have 517 in our curriculum. That's what that course is about, statistics. It's taking real data, fitting them to a given model. Right? Does that seem like it's becoming a little bit clearer why we go through all of this mathematics in wireless networking? And really, this methodology is at the core of wireless networking. Right? And this is why 503 has significant mathematical component to it, and why we teach you 503, why we insist that you take that in your master's curriculum, is that if you can understand this to the point where you don't feel like all of that math was just really complicated stuff, but you see that there's some value to it, that if you could find a model that describes your reality, if you could find the parameters to it by doing statistics, that you can then make a better design, because you can figure out how to optimize it, and you can understand how your systems perform. That's really important. And how to do that performance analysis, 503 teaches how to do a lot of these things in closed form, writing equations and expressions that are mathematical expressions. In the real world, often we don't write things down in closed form. We write programs that crunch out numbers for us, right? We simulate. But we will simulate based on the model that we have and the parameters that we have. So even if I'm creating, and you're going to do this, you're going to have NS3 as a simulator, and you're going to work with it, you will have to say, what is the traffic? Right? You might say it's going to be a Poisson traffic with a rate parameter lambda equal to, 5 packets per second. Okay? This whole process of measuring something in the real environment is how you would have figured that out in reality. But once you know that that's the parameter you're going to use, the simulator can go ahead and say, this is the performance of my system when the load is 5 packets per second. So this analysis doesn't have to be in closed form. It might be a simulation. Right. But you still need to know the basics of what are the models that are going in, how do you fit data to those models in order to be able to use these things in a real system. Okay, it's a little bit of a digression there, but I think it's really important. I think this is really the point of the class in many ways, is to teach you to think about network designs more rigorously, not just as I tried a bunch of things and it looks good or it doesn't look good, but you don't know what you're needing to do in order to evaluate your designs, how to figure out if your design is good, how to design a good system. So the other things we talked about were still kind of in recap mode. We talked about fast and slow fading. And we said that this has to do with coherence time or Doppler spread. And in the last class, we actually derived an expression for coherence time. We just defined it as some function of the parameters for a two-state Markov model. To be honest, when I did it last class, I did it just off the top of my head. I hadn't looked up any book to tell me what the coherence time is. And I did that on purpose. It may actually correspond to something in a textbook somewhere, or it may not. It doesn't really matter. Ultimately, you as an engineer, you as an analytical person looking at a design can sometimes make judgment calls yourself and say, I'm going to call this coherence time. And if somebody else later comes on and says, but this textbook says something else, you can say, oh, I understand. My definition was this, and this is what my plots tell me with respect to my definition. But at least you're clear on why you chose that definition. Right? Ultimately, whatever is in a textbook was somebody else's definition. It was all an art. Right? So God didn't hand down a definition of coherence time. Humans have done that. So that's, again, something you miss out sometimes when you take these mathematical courses. You think that what's in a textbook is somehow like fundamental. And a lot of times, especially in engineering, we're just defining what to call something. So we talked about fast and slow fading, and we kind of said, if you know the parameters for the two-state model, this is how you might define it. We talked about also flat versus frequency selective fading. Which has to do with something called delay spread or coherence bandwidth. And these things are duals of each other. When you have a high coherence time, you have a small Doppler spread. When you have a high Doppler spread, you have a low coherence time. This has to do with basically with mobility. How fast things are moving. The transmitter's moving, how fast the receiver's moving, how fast things in the environment are moving. Whether the environment is showing flat or frequency selective fading, this has to do with sort of the environment, and particularly the way I like to think of it is sort of how echoey the environment is. Right? Think of in our audio frequency, when you go into a cave versus when you're out in the open, you feel like there's something different about that cave environment because of all the echoes, right? Well, that's really what happens with RF also. Depending on the environment, certain environments are extremely reflective. You get a lot of multipath components that show up late. And when they show up later and later, you're increasing what's called the delay spread. And delay spread, we also said, has to do with this concept called intersymbol interference. And in particular, you should be aware that intersymbol interference generally shows up, is sort of a problem at high data rates. Why? Because your symbols are really close to each other. And there are different ways to deal with it. We talked about a couple in the last class. We said that CDMA, if you use certain direct sequence spread spectrum, sorry, no, I shouldn't really say CDMA. Let me be careful. If you use a direct sequence spread spectrum technique, CDMA is a special use of it for multi-axis environments. But in general, if you use a direct sequence spread spectrum technique, then if the code or the chip sequence is chosen carefully in such a way that time shifts of that sequence don't correlate well with the original sequence, then you can filter out these later arriving components and they don't show up and bother your system. And so that helps reduce the intersymbol interference. A different approach, which is also very widely used and perhaps these days increasingly widely used, is OFDM, in which we take the original stream and we split it into a bunch of subcarriers, each of which has a lower rate. Okay, and someone wrote to me was a little bit confused because when we do direct sequence spread spectrum, we're actually increasing the data rate, and here we're reducing the data rate in each subcarrier. And they were asking why in one case we increase, in one case we decrease it. In this case, in both cases, the actual data rate is still the same. It's whatever you want to send it at. In this case, we take that stream, we split it into a bunch of substreams. In the direct sequence spread spectrum, we don't split it into substreams. We keep it at that original data rate, that stream, and then we're multiplying it, or we are encoding it, if you will, with a spreading sequence which is at a faster rate. Okay, but that spreading sequence, or what you're sending with this spreading sequence, is not what you care to decode. You want to decode the original scheme. But the advantage of spread spectrum is that with this additional process of spreading and despreading, you can filter out the later arriving components if the sequence is chosen carefully. So it's a completely different approach to dealing with this problem. Okay. A different benefit of direct sequence spread spectrum is that that larger spectrum you're now going to occupy, because you're using a higher rate chip sequence, can be shared by a bunch of different sequences so long as they don't correlate well with each other, so long as they're orthogonal to each other. And that process is called CDMA. Okay, it's like you're giving different codes to different links. They don't correlate well with each other, so each of them doesn't, in some sense, see the signal from the other nodes. All of that is sort of treated as noise. The fast and slow fading environments have an impact on communication performance. At a minimum, if a channel is bad, how long is it going to stay bad is an important consideration in deciding when to retransmit. It's a consideration in deciding should you maybe sacrifice your data rate by using a higher, like a stronger error control code, because this channel is going to be bad for a long time. So you might as well use some code to improve your performance. So one example where channels stay bad for very, very long periods of time are deep space communication. So if you have a satellite that's sending data to a node on Earth, and you're, for whatever reason, you're really far, and on top of that, maybe there's some shadowing happening, you've gone behind a planet, or you've really just gone so far, the channels are not going to get better anytime soon. The only way for you to send data is not to wait till the channel becomes good again. That may take weeks, if not months. What you might be forced to do in that case is just code your data at a lower rate, which is to make it more resilient to errors. And now you get the data, you reduce the data rate, but your reliability is made possible. So in some sense, how long channels stay bad, that's an important consideration. And that's why we care whether you're dealing with fast fading or slow fading. Sometimes fast fading is a good thing, because if you have extremely fast fading, that means that if channels are good now or bad now, they're going to be good soon enough. So you can sort of time average your performance, and on average, things might look pretty good, even if at moments things are bad. So sometimes fast fading is not necessarily a bad thing. That's all really I wanted to say about these ways of looking at fading. Then we talked about CDMA, which is really using direct sequence spread spectrum for multiple access. More generally, we talked about two types of spread spectrum, DSSS as well as frequency hopping spread spectrum, and both of them are used in practice with or without, and DSS may or may not be used with multiple codes, in which case it's CDMA. We talked about OFDM briefly. We talked about error control coding. So these are all really sort of techniques that have been developed to improve performance in the presence of fading. Another important technique that is used to deal with the complexity of the wireless channel, its unreliability, its poor performance, is known as diversity. And more generally, beyond diversity, there's a class of techniques that have come to be known as MIMO. It stands for multiple input, multiple output. And generally speaking, we're talking about using multi-antenna systems. So let me talk about MIMO in general, and then maybe I'll come back to some specific examples of how the diversity advantage might work. So in general, when we call a system a MIMO system, we mean that at the transmitter end there are multiple transmitting antennas, and at the receiver end there are multiple receiving antennas. So let's take an example where there are 3 transmit antennas and 2 receive antennas. For notational convenience, let's call this M antennas and N M transmit antennas and N receive antennas. So the idea is that by having kind of different antennas, and typically they have to be spaced apart, on the order of, let's say, half a wavelength. So when I say half a wavelength, what that wavelength is depends on your carrier frequency. In most of the systems we use, these are on the order of centimeters, sometimes even larger if you're using a low frequency. Increasingly, a lot of research into 5G, for example, is looking at spectrum that will be really, really high, like instead of something on the order of 1 gigahertz, 2 gigahertz that we use now, maybe systems that operate at 60 gigahertz. Okay, and that's called a millimeter wave because the wavelength, the lambdas, are down to millimeters. And that's actually both an opportunity and a challenge. It's a challenge because your wavelengths are so small, your antennas have to be very sensitive. But it's an opportunity because now your antennas are so small, the wavelength is really small, you can have more antennas, right? So right now with existing cellular, your receivers can't really have very many antennas, maybe a couple of antennas in most cases, 2, 3 if you push, maybe a laptop could have 3 antennas on it. But if you were to operate at much higher frequencies, you could potentially fit dozens of antennas on the single receiver. So how many antennas you can have is somehow a function of the wavelength. Typically, base stations, cellular base stations, might use more transmit antennas because they're physically larger. They can have spacing depending on how large and what direction they're facing and what the size of the installation is. You might fit potentially 4, even 8 transmit antennas or something. Depends on the base station. So typically, these links are not symmetric. The number of transmit antennas and the receive antennas may not be the same because the transmitter might be larger. Device can physically fit more antennas. If you have 802.11n access point, you might see it has multiple antennas sticking out of it, and that's a MIMO based 802.11 system, and in most configurations like 4 transmit antennas and 1 or 2 at the receiver. Typically 2 at the receiver, I think. So you have more antennas, what's the big deal? So the simplest way to see why this is a good thing is if you just sort of draw these lines between every transmit antenna and every receive antenna. What you see is that what used to be just a single channel between the transmitter and receiver has now grown to m times n different channels. So in this example, 6 different lines. And this presents an opportunity. So very naively, you can imagine, let's take a very simple example where there's multiple transmit antennas and a single receive antenna, right? Here's the simplest thing you could imagine might happen is due to multipath effects, due to the phase shifts with which they're arriving, maybe 2 of these are undergoing a deep fade. But maybe the third one is not, right? So you can already see that there's potentially a benefit to having more antennas, in that some of these channels being bad doesn't mean all of them are bad. So as you move around, maybe at different places, different of these channels might look good. There's different ways of exploiting this diversity effect. Let's actually look at a case where we have kind of received diversity, because typically this is easier to see why you might benefit. So here's an example where there's 2 receiver antennas and a single transmit antenna. So now you've got one signal coming, another signal coming. So a couple of things you can do. One is called selection diversity. You could maybe measure the gain at the 2 receivers, and whichever signal has the better gain, that's the one you use. Right? So you basically create a little switch that measures the gain at the 2 of them, and then before you bring it to the receiver, you kind of measure the 2 gains. Whichever one has a louder signal, that's the one you pipe into the receiver. So that's called selection diversity. Pick the stronger signal. Now, intuitively, it should already be clear to you that having 2 is better than 1, right? Because now I have a choice. Before, if I only have one receiver, I have to take whatever it gives me. Now, if I have 2, if I have 3, if I have 4, as I increase the number of antennas, the likelihood that I'll get a strong signal on at least one of them gets higher and higher and higher. Right? So that's the way in which selection diversity would work. A different way of using diversity is called combination. The simplest type of combination is just equal combining. So equal combining, what you do is whatever signals you get in either of those branches, you just combine the signals together. It's like looking at the added signal, right? Now, first of all, it's not entirely trivial that this is going to be better, because not only are you adding the signal, you're also adding the noise. Okay, so figuring out what the effective SNR is going to be in this case is not obvious, and in particular, it's not going to be just double the SNR, right? Even if both of them were just as strong. But in many practical settings, this turns out to do quite well. In fact, this is one of the most common types of combining receivers that's implemented. You just take all the branches, whatever signals are coming in each of them, you just add them up. Okay. A more complicated receiver is called a maximum ratio combiner, which I'm going to talk about now. MRC. And the idea for a maximum ratio combiner is the following. So let's take the signals coming in. You have, let's just take a bunch of different branches. And what we're going to do is we are going to apply a phase shift. And we're also going to multiply it by some gain term. Let's call it alpha. And then we're going to take every one of these branches, and we're going to add them up to give us what's at the output. So something arrives from the transmitter at each of these receivers. You're going to put some phase shift to each of them, and you're going to multiply each signal by some gain value. So the intuition behind applying a phase shift is that these three branches may not be at the same distance from the sender, may be getting different multipath components of the signal, and so they may be not synchronized with each other in terms of phase. And if you take sort of an extreme case, maybe a couple of these are so out of sync with each other in terms of phase, they're exactly 180 degrees apart. So the signal arrives from both of those branches and just immediately would cancel out if you were just to add them without a phase shift. So the idea of the phase shift is if I could measure at each of these receive antennas what the phase is and I can correct for that, then I can get all of these three at this point to be all synchronized with each other. So whatever the phase shift was, I've corrected it. So the goal is, right, all branches are synchronized. Now, the gain is kind of an interesting piece here. So if I get a branch which has a higher SNR and another branch which has a lower SNR, intuitively the branch with the lower SNR is contributing less signal and more noise. The branch with the higher SNR is contributing a lot of signal, relatively lower noise, and so on. And so the question is, how much should I weigh what I'm observing on each of these channels, right? One extreme is selection diversity. In selection diversity, I put the gain to be 1 in one of these and 0 in the others. So whoever has the highest SNR, I just pull that one out, right? But it turns out that's not necessarily the best thing I can do, right? With the equal gain combiner or equal combiner that I mentioned before, we're just setting the same value to all of these and we're just adding them all up. It turns out that's also not the best thing to do. So what's the right choice of these gains so that what we get is as strong as possible? That's sort of the question we're trying to answer. Right? So imagine that we get some SNR gamma 1 coming into this place, some SNR gamma 2 coming in here, some SNR gamma 3 coming in here. What's the combination of these that will give us the highest signal is sort of the question here. So in fact, let's not talk about, so the gain is being applied to the signal and not the power. So let's say this corresponds to some amplitude A1. Right, so this corresponds to some amplitude A1. This corresponds to some amplitude A1. So on branch 1, the SNR is like A1 squared over the noise squared. For simplicity, I'm going to assume the noise is the same on each branch. On the second branch, I'm getting an SNR of A2 squared over N squared. On the third branch, I'm getting like A3 squared over N squared, if I were to just look at the SNR at these points. But what I'm actually going to be able to do if I apply this gain-based combiner is I can get at the output of each of these alpha 1 A1 squared over N squared, alpha 2 A2 squared over N squared, alpha 3 A3 squared over N squared. Right? And if I add up all of these signals together, ultimately, we're basically trying to figure out what is the however many branches you have, what's the choice of alpha such that you're maximizing this overall SNR. So this is sort of the total SNR. So it's an exercise in calculus. It's a multivariable optimization. We can choose these alpha values, and we want to know what's this combination of alpha values for which this term would be maximized. And when you work it out, what you end up finding out is that the alpha i's will be proportional to ai. In other words, the branch with a certain signal ai, signal amplitude AI, should have a gain AI associated with it that's proportional to the signal. So the branch with a larger signal should get a larger gain. You should get more of it. You should weigh it more, right? And the branch with, let's say, A3 happens to have the A2, A3. The branch with the smallest amplitude should have the smallest gain applied to it, meaning you get the least amount of signal from that branch. Scale it in such a way. So this choice of the gain, so this is the gain, right? This is the signal amplitude. By applying this, you get maximizes the output SNR. So in other words, the best choice of alpha I is not of alpha I is not to set it equal to 1 for one branch and 0 for the other, or to set it equal to all of them. It's to look at the signal amplitude and set it proportional to that. So the stronger signals you take more of, the weaker signals you take less of. And by applying this amplitude, you're also sort of absorbing correspondingly less of the noise coming in from that channel. So we might go through this derivation if we need it in a homework assignment. Otherwise, I'm happy to just leave it at this. The one thing you should know is that this particular diversity scheme is called maximum ratio combining, or MRC. And that in this case, you can show that the output SNR, expected SNR out, would be equal to L times the expected SNR for each branch, right? For each branch. So it's effectively as if you're getting a boost in your overall SNR performance. And as you can imagine, the more antennas you have, that's what L is the number of antennas. If you're increasing the number of antennas and you're getting a boost in your SNR performance based on that, then your error rate performance is going to improve as well. Okay. And more generally, you can show that the error rate becomes sort of proportional to 1 over SNR to the power L. And sometimes this is, for that reason, called the diversity order. And this is true at sort of at high SNR values. There's some approximation here at high SNR values. So intuitively, then, the more branches you have, if you use maximum ratio combining, you're getting a overall signal boost or a lower error rate. That's one way in which you can benefit by having more antennas. And this example I gave you was for a receive antenna system, and we worked out some of the details. In general, the diversity order L is, or let's say the maximum diversity order L is equal to M times N. So if I have a system where I have multiple transmit antennas, multiple receive antennas, the product of these, which is basically the number of different channels I have, that's what's going to give me the diversity order. And especially at high SNR values, I'm able to translate that into improvements in my error rate. So that's one way in which a MIMO system helps you, because now you have more antennas, you can translate that to a more effective SNR at the receiver, and therefore lower error rate. Okay, so that's one benefit. This is called the diversity benefit. So more channels implies higher effective SNR and lower error rate. There's a different benefit you can get from a MIMO system, which is called the multiplexing benefit. Which is more antennas can be translated to throughput improvements. So what does that mean? Throughput improvements. So there's a result that says that the capacity of an M by N MIMO system is sort of at high SNR over, certain, assuming there's some fading and everything, scales roughly speaking as the minimum of M comma N times log so high SNR, so we can think of it as just SNR. Right? So you know that typically in Shannon's equation it's like a log of 1 plus SNR. If it's a high SNR term, that 1 is negligible. So this term is just like that. The term in front of it is a rate improvement. It's saying on one channel I can get like a log SNR. If I have an M by N MIMO system, the maximum throughput I could get out of it is potentially the minimum of M and N times this. Okay. So what do I mean by minimum of M and N? Is if I have, for example, a 3 by 3 MIMO system, right? So this minimum would just be 3. If I have a 3 by 2 system, however, this would be 2, right? So in other words, for getting this throughput improvement, what matters is not the product of those two numbers. It's not the total number of channels, but actually it turns out what matters is the rank of the channel matrix, which I won't get into very deeply here, but the minimum of the number of transmitted receiver antennas, that's how much throughput improvement you might be able to get. So one thing, just to build a little bit of intuition about why might you even get such a thing, let's just take a look at an example. So in a single channel system, if you describe what is the gain of that channel, it's just, if you have a transmit antenna and you have a receive antenna, this link, whatever the gain of this link is, let's call that H, that's the full description of the channel. In a MIMO system, if I have this 2 by 2 system, I have a transmitter 1, I have a transmitter 2, I have a receiver 1 and a receiver 2. Then I have these 4 different channels, and basically there are gains corresponding to each of them. So I can kind of describe the channel as a matrix. Right? And actually the channel can be described as a complex matrix because these H's are capturing maybe the gain of the channel, but also the phase shift of the channel. But this description of the channel in a MIMO system, it's called a MIMO channel matrix. And I feel like it's out of scope for this class, but certainly if you took 535, you would see that if you have a matrix to work with, there are ways that you can decompose this matrix to create effectively 2 virtual channels. It's as if you're able to convert this into some, imagine A1, A2, 0, 0 here. Actually, what technically you do is there's another matrix up here, another matrix over here. So you can always take such a matrix, decompose it into 3 matrices, the inside of which is a diagonal matrix. And it's as if in this matrix, whatever was being sent was being received by this receiver, and whatever was being sent by this sender was being received by this receiver. It's as if you got like 2 virtual channels, right? There's a lot of details here. It uses something called singular vector decomposition, which requires knowledge of 441, for example. But the point is that there are these matrix calculation techniques that take this MIMO matrix and convert it into a diagonal matrix of a certain size. How large this diagonal matrix is and how many entries it has is basically the minimum of M and N. That's how many diagonal entries you'll have. That's how many virtual channels you're able to create out of your multiple channels. So the challenge here is that whatever is being received is sort of all mixed up, right? Whatever this guy's sending is going not only to this receiver, it's also going to this receiver. Whatever is being sent from this antenna is going to both receivers, and it's all getting mixed up, right? But when you do this SVD decomposition, there's a way to pre-code what you send at the sender and a way to sort of post-code what you get at the receiver, so that effectively it's as if this transmitter, not this transmitter, but sort of a virtual transmitter is talking to a virtual receiver, and another virtual transmitter is talking to another virtual receiver. And each of those 2 virtual channels can be sent separately. And it's as if all of a sudden, instead of just having one stream of data going from the sender to receiver, you're able to send 2 parallel streams over the MIMO channel. And that's what's giving you this rate improvement. So this particular SVD-based use of a MIMO channel is one technique people use for increasing the data rate on a MIMO channel. It doesn't always work. It depends on some of the characteristics of the channel matrix itself. In that one of these virtual channels might have a stronger link than another. It typically works well when you have very high SNR. And the third thing to know is that you can simultaneously derive the maximum throughput advantage or multiplexing advantage out of a MIMO system, as well as the diversity advantage. So there's something in MIMO called the diversity multiplexing trade-off. So recall that we said something like, the maximum diversity is like M times N, where what I mean by diversity is kind of what is the scaling of the SNR exponent as I increase SNR for the probability of error. So this basically has to do with error rates. The maximum multiplexing scales as the minimum of M and N. And what can be shown is that if we have a multiplexing gain of R, then roughly speaking, the diversity gain scales as M minus R times N minus R. So what is this trying to say? It's trying to say, like, let's take an example. Let's take a concrete example. So let's say we have a 4x4 system, right? I could either have sort of diversity gain of 4 times 4, which is 16, in which case I don't get any multiplexing gain at all. Or I get a multiplexing gain of 4, in which case I don't get any diversity gain at all. Or I can take 2 degrees of freedom and apply that to multiplexing gain. So maybe I can get a multiplexing gain of a factor of 2. And then I can only get a 4 minus 2 times a 4 minus 2, which is a factor of 4 diversity gain, right? So example, so I can get sort of, diversity gain of 16 and multiplexing gain of, they call it 0, but basically no improvement in the multiplexing. It's as if each channel was just as is. So, right. Or you can get a diversity. You can get a multiplexing gain of a factor of 2, and a diversity gain of 4. Or on the extreme case, you can get is a multiplexing gain of, so I shouldn't call it M, maybe let's call it like GM or something, multiplexing gain, and call this diversity gain. So just to clarify, what we mean by this is basically like a single channel. Whereas when I say 2, I just mean like a factor of 2 improvement in rate, a factor of 4 improvement in rate. And here, the diversity gain has to do with like the error exponent being either 4 or 16. So the point is you can get both simultaneously. So typically if you have a MIMO antenna system, they have different ways in which you can configure it, either to improve your data rates or to improve your error, but not both. Or at least not both simultaneously. So if you were to kind of try and plot this, you'll see, multiplexing gain, which is a throughput improvement, and a diversity gain, which is really an error rate improvement. And there's just some decreasing trend here, where if you get more and more throughput, you get less and less improvement in error rate. And this trade-off between throughput and error rate we've seen before. So here the assumption is that the power is fixed. So if I fix the power, there's this trade-off between throughput and error rate. And that's sort of a classic result called the MIMO diversity multiplexing trade-off. So even if you look at practical MIMO based Wi-Fi systems, you'll see that they have different modes at which they offer different throughputs, and they basically have to do with what the SNR is, right? So if the SNR is high, you don't care about an error rate improvement, you might want to get multiplexing improvement. If the SNR is relatively low, you would like to get error rate improvement because the channel is kind of noisy, then you divert some of the MIMO resources to help you improve the error performance of your system. So that's one thing that's kind of unique to MIMO systems. So that's all I had to say about the physical layer, really. One other problem in your homework that I might spend some time on since we have it, there's also a problem for estimating the parameters of a two-state Markov chain from data. And imagine, and I think in that data set I've given a threshold for you to figure out when to call the channel bad, when to call it good, so you have zeros and ones. So imagine you basically have a string of zeros and ones, right? You have a large number of these. And so the question is, I have this data set, how do I estimate the parameters of this model from the data set? So in statistics, there is a whole class of approaches that go under estimation theory that are called maximum likelihood estimates. And roughly speaking, what they're trying to say is, for what value of P01 and P11 do you maximize the probability that this is the sequence you would observe? Does that make sense? So you're basically saying, I can choose my model to be different numbers, so I can, pick different values for two of these. And if I choose different values of these, I can say, how likely is it that I observe this sequence? Okay. If I choose a different value for P01 and P10, I might get a different value for the sequence, and so on. And so trying out different values of P01 and P10, I get different probabilities that this was the observed sequence. And I would like to pick as my values for P01 and P10 the most likely estimates, or the maximum likelihood estimates. So basically it's asking the question, for what value of P01 and P10 is the observed sequence most likely? And it turns out that for a simple Markov chain where you have all of the observations, the maximum likelihood estimate to figure out what P01 and P10 is a very intuitive estimate. It's almost like the first thing you would think of. Any guesses what it might be? So if I just gave you a bunch of zeros and ones and asked you to estimate what these might be, what would be like a very intuitive thing you might come up with? You're saying something? Just count the changes. Right? That's the simplest thing you could do. How often does a 0 get followed by a 0 versus how often does it get followed by a 1? So the number of times it gets followed by a 1 versus the number of times it gets followed by a 0, you take the ratio of the number of times it transitions into 1, you call that the probability. So if you were to take probability of going from a 0 to a 1, or we're actually calling it P01, you simply count the number of times that you see 0, 1 transitions over all the number of times that 0 shows up, right? So every time a 0 is observed, it could be followed by either a 0 or a 1. You count every time you have a 0, how many of those translated to a 1. That's the probability that you go to a 1. And of course, you can verify that this is a reasonable estimate because P00, which would be the number of times 0 goes to a 0 over the number of times 0 is observed. Clearly, this plus this add up to all of the possible ways in which 0 is observed, and therefore these two add up to 1. Right? So clearly. And similarly for P10 and P11. Okay? So it's a very intuitive way of estimating the probabilities. But what I'm saying here is that, in fact, it turns out to be something that you can justify mathematically as being a good way of estimating the probabilities. It's the particular way in which you could take these observations and use them to come up with probabilities that maximizes over all the probabilities you could have estimated for P01 and P10, all the values you could have estimated, it maximizes the chance that this is what you observe. Okay, this is not a trivial statement. In general, for a problem, deriving the maximum likelihood estimate may not yield a trivially obvious and intuitive rule. But for the problem of a Markov chain with all of the observations, it is that simple. It turns out to be a very natural way of estimating it. Sometimes you encounter problems that are a little bit more complicated. So for example, currently in a piece of research that we're doing, we have a scenario where we are trying to estimate these probabilities for a two-state Markov chain, but we're missing observations. Right? So sometimes you don't even see what the value is. It may be a 1, maybe 0, I just don't know. Then it gets a little bit trickier to figure out how I should count. Right? So then I have some missing observations. Should I take those into account? Should I take into account that, if it's missing in one time step, what's the probability I went from 1 to 1 after 2 time steps or 3? So it gets a little bit more messy in other cases, but in this particular case, it's very easy. So one of the problems in the assignment asks you to estimate the parameters from the data, and you just use this estimate. I think that's all I have for today. I wanted to mention a little bit in advance that there is no class on June 13th. We will pre-tape a lecture. And then on June 15th, the TA will teach how to do NS3 simulations. And I strongly encourage everyone to show up to this class because he might do it as a hands-on class where you bring in your own laptops with the NS3 installation. He kind of walks you through how to do simulations on it. In particular of wireless networks, right? That's about it. So there is a homework 2 that's due this Friday, and I'm hoping to post another homework that'll be due next Friday. That might be a little bit lighter at this point. Okay? Thanks.
This concludes EE 597 with Professor Krishnamachari on Wednesday, June 1st, 2016.